Okay, so I will ask the first question. So regarding your very nice homogenization model, when you compare, the effective cylinder with a cylinder where you have 20 plates, I can still see some slight differences. Yeah, here. So do you think that some kind of higher order homogenization would make this? I mean, what is the origin of this difference in your opinion?
It's just what you might imagine. In the one system, you have a discrete description of the problem. Actually, yeah, there's also there were difficulties doing the CFD, the picture on the right. Okay, the CFD picture. We couldn't make I didn't do this, Sim did, but we couldn't make the barriers as thin. They could only, they occupied 20% of the, there was, for every meter, there was 20 centimeters of barrier. They had to be thick in order for the CFD to work.
Okay, I've got another question. So in your homogenization method, your plates, they are just segments. They are just, lines with endpoints. So, and these segments, they have a varying, they are varying interval, they have a varying length. So,
like this.
Yeah, exactly. And so, of course, in the model of your collaborator, each segment is now a plate. And what does it take for the, corners, the top and bottom of the plate? Is it curved? Is it straight?
So the plates just end in a point, right?
Yeah, but in his model.
Oh, here,
yeah.
Over here. Well, you can see that these plates have thickness, right?
Yeah, but they are curved. The end boundary. So they are curved boundary or they are straight boundaries, because this might be the origin of the difference as well, no?
I think that has a significant. I mean, let me just say we've done some.
Yeah.
I haven't got them here, but since then we've got on the most recent piece of work. We've also got some more CFD, which is actually applied to very thin plates, specifically to thin plates, and that works. I didn't show those results, but they work a lot. They have much better agreement. You see here. So I think it's to do with two things. One is the thickness, and one is probably what you say. It's to do with the fact that the ends here are not very clear what they're doing.
And I've got another question. In this model, in your model, do you have any artificial dissipation to make the model converge? I mean, is your model something which converges very fast, or you need a very high truncation order to reach the convergence of your solution?
So it depends upon the situation. So really, the number of the truncation of the system depends upon essentially how much variation you see around the cylinder, right? So it's really like a Fourier mode. So here you might only need 8 or 10 modes, for example. But here, the difference is the functional variation as you go around the circle is there's a lot more variation, so you need more modes here, and here you need even more modes. So the answer is you need as many modes as you need to resolve the variation in the function. I haven't shown you any results here with damping in them, apart from these curves. I mean, if you put damping in, if you put a small amount of damping in, you need still quite a lot of modes. Because you still have very high resonance with a very small amount of damping. You can get convergence, but you still have large variations as you go around the cylinder, so you need a large number of modes. With high damping, you need fewer modes because you excite a lower resonance, so you have less variation to resolve. That's sort of like briefly what happens.
Okay, thank you so much. Perhaps you have a question? I see you are on the screen.
Yeah, so can you hear me okay?
Yeah, I can.
Yeah, we can.
Yeah, so it's just that, yeah, with what you were saying with the damping, when I wrote up the same system as well, I was finding like what Richard was just saying, that you do need a lower number, but it's still of the order of like, I mean, at least maybe like I was using 70 or 80 even sometimes for above resonance. But what I was wondering is what kind of damping, what size of damping are you using? Because I've just been sticking with like 10 to the minus 3. I don't know if that's really large or really small relative to what you're using.
10 to the minus 3, I would say, was quite small. Yeah.
Yeah.
I was working around 0.1, 0.01. That was
right.
I mean, I was just playing around because I didn't have a particular purpose for it in mind.
Yeah, exactly.
But from recollection, I would say that 10 to the minus 3 would be small enough that you'd need probably of the order of what you say 70 or 100 terms in the expansion to get something close to convergence. It's quite hard work numerically to do that.
Yeah. Yeah, it was.
Then, following the question of Henry, I mean, so you reach convergence for a given dissipation, but your convergence is not so robust with respect to dissipation, or is it? I mean, the result you get when you vary this kind of dissipation, how much does it change?
Gosh.
I mean, is it something which is really, sensitive, or is it a mild, is it a rapid transition, or is it a mild transition, a smooth transition?
I mean, are you asking about the number of terms that you require, or when you talk about convergence, you're talking about whether or not?
Because in fact, I guess that when you want to check your convergence, so you change the truncation, and you check that after certain truncation, you have some kind of stable solution.
Yeah.
So, but then, have you looked at how much this varies with respect to, the small dissipation?
I can't think that I did this for the particular case of the cylinder. I've done it in the case of a waveguide with the stuff I talked about at Imperial a month ago.
Yeah.
And there I got convergence. So as the dissipation tends to 0, my solutions were tending tending uniformly to a solution. Okay, so I needed some dissipation. As the dissipation tended to 0, my solution were converging to a solution which isn't a solution without. I mean, this doesn't have any. So it's like a non-uniform limit, right?
Okay.
I couldn't get to 0 dissipation, because at 0 dissipation I get no convergence at all.
Yeah.
But if I take the dissipation and I make it smaller and smaller and smaller, I was getting to convergence to, let's just say it looks like this. I was getting convergence to a solution. Yeah.
So it's just that the solution for the totally non-dissipative case is so singular that you can't get it.
Exactly. Yeah.
Uh-huh.
I mean, my feeling is that there's problems with this business here. Effective matching conditions assume, okay, that when you do the homogenization, you assume that you have sort of local periodicity as you move across here, right? That's how you do homogenization. You assume that there's a local variable and a global variable, and the global variable doesn't change much with that. On the scale of the local variable, it's basically periodic. That's what you do in homogenization. And I think the problem is that breaks down, okay, when you have a situation like this, because this is no longer continuous and periodic. You suddenly hit this resonant channel, okay, and that breaks down these effective matching conditions. I don't know if I explained that particularly well, but I think there's these effective matching conditions are designed for a situation where everything is nice and smooth, and they don't work when the solution isn't nice and smooth, but it has these kind of nasty singularities. And damping has the effect of smoothing those out, and so homogenization now works again. So you have this kind of conflict between the two situations.
Can I ask one last question on this?
Sure, of course, as many as you want.
It's just that, have you looked at all at trap modes in singly periodic structures? Yeah, for these cylinders, or have you just looked at the scattering of incident waves?
No, I've only looked at the only thing I've done with cylinders is what you see here. So yeah, there's nothing. I mean, there's all kinds of interesting problems that you could do. So you could put an infinite periodic array of these in a line, and you could ask yourself, well, how do these support trap modes? Or essentially, that's the same as putting one in a channel, and does it support a trap mode?
Yeah.
And how much energy can you store inside these cylinders, and can you play around with the parameters? But so there are lots of things that you could do, yeah, but I haven't looked at anything other than what you see here.
Yeah, I've had a look at the circular trap modes on the the whispering block modes, if you like. I'll email you about that later. Yeah.
Any more question, Henry? No. Please, people, come forward with your questions, because it's a fascinating object. I mean, I think Richard introduced a very new type of metamaterial. I mean, it's really fascinating, this meta cylinder.
I should have spoken more about the cylinder and less about the rest of the stuff.
No. All the stuff is really interesting. By the way, going back, to your curved waveguide. Of course, in your case, it's curved, but it's a little bit reminiscent of also the water wave experiment of Agnès, when she has, this. Can you say a little bit more about that? In your cave, it's curved, it's smooth, but in your cave, it's like, a step.
Yeah, I mean, I did this problem entirely because of what you say. There's this previous paper going back to 2013, I think with Vincent Pagnuron as well.
Yeah.
And they looked at, instead of it being curved, there was an abrupt change of direction. So it goes through a sharp angle.
Yeah.
And it was the same kind of thing. There was just there was a coordinate transformation. Essentially, you just basically do a coordinate transformation to move the waveguide at an angle. And so again, it predicted perfect transmission. Actually, that's got more, strangely, to do with this problem here.
Yes, that's right.
Because they were using a metamaterial bed which looked like this ridge structure here. And essentially what they were doing was sending in waves through a waveguide at an angle theta naught, and sending out waves at a different angle theta 1. So it was just, it was actually just like refraction over the bed from left to right, as I described here.
Yeah.
And they produced perfect, so it was a perfect transmitter. And that's basically what I talked about here. This perfect transmission that you see in this picture here could have been you see it goes through an angle and then gets redirected in a different direction. You can think about putting this in a channel. So you can imagine this wave has been perfectly transmitted through like a Z bend in a channel.
Yeah. Okay.
Hi, Sebastian. Can I ask a question?
Of course.
Yeah, I should mention that my internet broke down for the question part, so it's very possible that my question was already asked. So let me know if that's the case. Can I go back to the cylinder problem, please?
Yeah.
Yeah. So there is no reason to expect in this case, I would guess, that without dissipation, anything actually blows up in the non-homogenized version of the problem, right? You have damping to infinity, so everything should behave fairly well. Is that, do you agree with that, or?
So you're saying in the discrete case, you shouldn't get a singularity?
In the, yeah.
This would be perfectly well behaved, this
Yeah, yeah.
discrete system. Yeah, it's the homogenized system which causes the problems.
Yeah, so I guess that I just got logged in when you were explaining this, but I think you explained that you have short variations, and that's why the homogenization fails.
Uh-huh.
So is it the case that when you just get to the frequency corresponding to the resonance of the widest, the longest channel, you essentially have a mode which is dominated by that channel, and everywhere else the wave field is relatively small, right?
Exactly so. Yeah.
Okay. So isn't it possible to analyze it based on that? So obviously it's not a homogenized limit, a homogenization limit, but isn't that sort of similar to analyses we both done in the past, where you have a single channel and you have a wave field amplified there?
It is, and yeah. So you'd imagine that you could do this using matched asymptotic expansions, right? You could just say, well, okay, I know what this mode looks like here, right? It looks like a cos or something like that. And
I would expect
I can do a local expansion here, and I can, match to a far field, and I ought to be able to extract all of the relevant information about what happens.
I'm not so sure it's really similar to the analyses we've both done with a single channel, because I guess if in the limit, if you're also in the limit where you have a lot of these plates, then the length of these plates close to the center is almost the same. So you have to take that into account as well. So you have to look at a very subtle limit, I guess, where the resonance is living in a sort of neighborhood of the central channel, and try to go from there.
Yeah.
So I would say, Richard, that what you might need is a homogenization theory, but like a resonance on resonance homogenization theory, where the long scale is actually not the scale of the whole cylinder, but sort of distinguished scaling that describes the region close to the central channel.
Yeah,
So
I'm sure.
you'd have a short scale, which is still the slot, but the long scale would be intermediate between that short scale and the diameter of the cylinder.
Yeah, I mean,
And of course, then you have the external region as well.
yeah. It's just not. I mean, I just don't know what to do with the fact that, I mean, if this was just an opening, right? Just like a single channel opening out into a half space. I mean, you and I know, how to do that problem. I think the difficulty I have, and maybe you know how to deal with this, is the fact that you have neighbors. And the local flow problem, it's not quite clear how you just solve in one channel and represent the effect of close neighbors simultaneously, and they must have an effect, because if this is near resonant, then this is near resonant, or if this is resonant, then this is certainly very near. I mean, you have a local effect here. I mean, you may have essentially flow coming down here and returning back up. This is not just a passive channel. The neighboring channels, they play. I believe they play an active part. And finding a mathematical description on a local scale that refines all of those different things, I've not understood how to do that. But I'm quite happy for you to tell me that there's a good way of doing it. I'd be very interested in knowing how to.
I have no idea. I haven't tried, but it seems like an interesting problem. One thing sort of similar that I've seen, if you have these two channels close to each other, then, if you have one channel, as we know, it looks like a line singularity in the outer region. But actually, if you have like two, they're both on resonance but out of phase, you can have a cancellation of that line singularity and it becomes a higher order singularity, so that the
You get a
radiation
dipole.
damping becomes weaker, and then you get a stronger resonance. So,
Yeah,
as you say, it can be very important, the fact that the channels are communicating on the
well, exactly so. So if you just take two channels embedded in a wall close together, very narrow, right? You can get a dipole effect, right? So you can get essentially, rather than a monopole effect, if there's another way of putting it, essentially where you get you get transfer of energy or fluid or whatever it might be between these two channels communicating with one another.
Yeah.
The fact that these are very, very slightly different lengths, I mean, there's you know, I'm just not intelligent enough to work out what to do, right? As soon as one works out what the right mathematical framework is to attack these problems, you stand a chance. But I think the difficulty is trying to work out how to set this whole thing up, and I just haven't been able to do that.
Yeah, I think it's probably the challenge of setting it up with the right scales and so on. And then, as you say, because they're not exactly the right length and they interact with each other, it will probably also entail technical challenges of solving potential flow problems, which are more complicated than we would like to solve.
Yeah, but I think it's an interesting problem, and I think there's an answer out there. But yeah, I think it's going to take some hard work.
You mentioned that you're looking at the damping as a function of the spacing.
Mm-hmm.
I don't know if that's proving fruitful or not.
Oh, I mean, I mentioned that I was thinking about using a physical model, right? Which takes into account the physical source of damping. So if you're in an acoustic situation here, you know something about the damping relating to, for example, the spacing between the plates. And there's a problem of, I mean, potentially there's a problem here with homogenization, that essentially what you want is to take the limit as the distance between these two plates tends to zero, and you want that to be a uniform limit. I mean, that's what homogenization is designed to do, right? That you make this distance a half and then another half, and that you're going to converge to some limit. And that relies upon the damping. If you introduce damping, the damping being consistent with that uniform approach. If the damping somehow is not just a simple, straightforward, if it doesn't fall into line in the right way, then your damping will be dependent upon the width between. If the damping is dependent on the width between the channels, right, then the limit is not going to be. It's going to be a bit awkward. You see what I mean? Sorry, I got sort of upside down and back to front with that. It's gone quiet. Does that mean everybody's gone, or have I lost the internet?
No. We are all
Thank
here.
you. Yeah.
It's just
very interested.
no. It's just that I'm at the mercy of our IT services and their wacky way in which they set up our network. Sometimes it just disappears.
So it was very, very interesting what Ori described. So again, I'm sorry to insist so much. So with your model as it stands, can we expect a relatively good match between the finite element model, let's say, and your effective model, provided we have many very thin plates and we add just a little bit of dissipation, but you say that this dissipation should be at least on the order of 0.01.
My general advice is that if you're away from resonance, if you're away from resonance, you should be absolutely fine. You don't need any damping. Your finite element model, something looking like this, will compare well with a homogenized model. Okay, so if you're not at resonance, you will get good agreement between the two models. So this is not at resonance. If you are at resonance, this temptation is to add damping to this model. What I'm suggesting is that so I don't know how you add damping into a finite element model. I mean, I don't know whether how that's done, but if you want agreement between these two, then you need consistency about how the damping is added to the homogenized model and the way that it's added to the finite element model. You can't just 0.01 as a number, doesn't really mean much. You see what I mean?
You know.
Well, sorry, can I step in
Yeah.
for a moment, Sebastian? I was just going to say that if you're going to, you can also write down this problem in acoustics.
Yes.
And then in acoustics, it's pretty easy to get consistency between the damping in the finite element method and in your homogenized model.
Okay. Yeah, because I don't know anything about the finite element
model. In contrast to water waves, I mean.
But in fact, we've been trying that to be, in fact, in the context of electromagnetics, we have an electromagnetic problem in mind, and we faced some challenges to get, I mean, we get similar plots with effective, so
what
effective model, yes.
Are you putting a dielectric in between the two? Have you got, are these perfect?
No, these are metallic sheet in air. So you have air, vacuum all over the place, except that you have metallic sheet.
So you've got perfectly electric conducting on these barriers.
It's Neumann. It's Neumann, just like you.
Okay.
And
how do you add damping then? Do you put a dielectric in between?
Oh yeah, it means that I add it's like dissipative air. It's just, you know, instead of having a refractive index for air, which is 1, it's 1 plus I delta. Okay, I'm just it's a thought problem. It's a thought experiment. Okay, I'm having dissipative air, and just to make sure that I can get a good match. It's a thought experiment, it's something is just, and the point is that, in the past I faced similar issues, but with sign shifting media. When you have a sign shifting media in the negative refractive index medium, you always add a bit of dissipation. So for instance, to model with finite element the perfect lens, you have the refractive index, which is -1 plus I delta, where delta actually I take, but on the order of 10 to the minus 10 or 10 to the minus even 20. But here you're telling me that your delta should be on the order of 10 to the minus 1, 10 to the minus 2, you see?
Well, it's just this balance in the homogenized version. It's this balance between taking a small amount of damping and a large number of modes that are required in the truncation of the infinite system. And if you want to get convergence in the truncation of the infinite system, you can't take your damping to be too small.
Yeah.
So that's the numerical issue that you've got over here.
Yeah. Okay.
If you're just adding if you're just adding I delta to the finite element method in the gaps, I think that's probably the same as just adding. I can't see that that's any different to what Henry will be doing in this system here, just adding I delta to his homogenized version. I think that's the same. They should. I just off the top of my head, I can't see why they shouldn't give you the same results.
We were seeing very similar results below resonance, comparing the finite element to the homogenization. Just like in Siming Zhang's work. So I think, Sebastian, we can talk later about trying it above resonance and talking about the damping a bit more.
No,
I have to go meet my supervisor now, so I just wanted to say thank you very much, Richard.
Okay.
It's fantastic. I think, you know, the object itself, I mean, and you can see you raise the interest of Ori and so on, so you raise the interest of mathematicians as well, but the object, the physical object itself is really a fascinating object. I mean, of course, what's nice is that you can make, you know, crystal fibers out of it. And I mean, it's really lovely, you know, because it brings so many new features. It's adding a new scale, an extra scale to your usual metamaterials, if you wish.
Yeah, I mean, it's rather similar to the double periodic array of posts. It's just that the posts have got very long and thin, and they've joined up to one another, right? It's like a dashed line where the dashes have got so long that they form a continuous line. I mean, it's not that far removed from what people have done before with, you know, doubly periodic arrays.
Yeah, but no, the object, I mean, the fact that your object is singular in many respects, so mathematically and also in terms of the design, no, interesting.
Cool.
Okay, so do we have, I'm sure we have many more questions. I mean, I can see that there is Philippe Petitjean, for instance. Philippe, it would be great to have a question from the water wave side. Okay.
Okay, perhaps may I ask a small
sure.
question?
Yeah, of course, Michele, that would be great. Thanks.
So this cylinder is a sort of an isotropy. So in terms of resonance, it gives, I'm trying to catch a sort of an isotropic effect in one direction or the other. Or is only the eigenmode that it creates?
Sorry, I didn't catch the question there.
Okay, so this cylinder has this barrier, and it creates a sort of anisotropy, no?
Absolutely, yeah. So the waves can just travel straight through in one direction. The waves just travel straight through. Yeah.
I expect that if it is isotropic, the eigenmode does not depend on the direction of the flow. The internal resonances. Here, you have resonances which depends on the direction of the flow. This is the question.
Yeah, that sounds. I've not thought of them in terms of eigenmodes, but yeah, that sounds reasonable. What you've just said sounds like a reasonable way of thinking about it. Yes.
And also the frequency does not depend on the direction of the flow.
Oh, I don't know.
Okay, it would be nice to investigate.
Sure.
The other question if you have connected the resonance frequency with the geometrical parameters of the cylinder, the radius, the distance, the height, something like that. As an engineer, this is the first idea that comes out.
Yeah, so yeah, I mean the resonance, I mean, so the cylinder just becomes resonant as soon as you've got this criteria is satisfied. Suddenly you hit resonance in the cylinder, and K is just the wave number, right? So if you know the height of the cylinder and the radius, then you can work out this criteria.
Irrespective
so this is
of the orientation?
That's irrespective of the orientation, yeah.
Okay, so it seems independent on the direction of the flow.
Yeah, you will always get these resonances independent upon theta naught. It will only be when theta naught equals 0 that you don't see this, because you have this strange transparency at theta naught. Sorry, it's vertical. It's 90 degrees in this diagram.
And I think that Philippe wants to ask a question as well. Hi, Philippe. Thanks a lot.
Okay, thank you.
There was a time when I was not there, so I'm not sure you already maybe answered the question, but it was on the experimental part. If we want to do some experiments there, how the dissipation, for instance, any kind of dissipation, it could be the weighting on the plates and things like that, could disturb everything. Do you have any information on that? People who did some experiments on this particular case?
So nobody's, as far as I know, done any experiments on this particular cylindrical plate array. Most recently, Vincent Pagneux has done some experiments that he showed me some results for a similar setup, plate arrays, but without this resonant phenomenon. So
in
this
water,
was
you mean? In water, in a water channel?
in water, yeah.
Yeah, so it's actually what we did here. It's on the deviation, right? Something like that?
Sorry, I don't see who's talking, so I'm trying to work out from the voice who it is that's talking. Who's this?
What?
It's Philippe Petitjean. Philippe Petitjean talks.
Philippe Petitjean. Oh, sorry. Yeah. Okay. So I don't know if Vincent Pagneux is still on the call, but he's done some water wave experiments to do with plate arrays, and based upon some work that I didn't show here, but which sort of complements this work, which is to do with negative refraction due to a plate array cascade, and you can place it in a waveguide and you can redirect waves perfectly. It's actually rather similar. It's a specific example of one of these things here, wherever they were.
Okay, so actually it's an experiment we did here in a few days, just before the end of an internship of a student, and we are going to start again next week. So you may have some more. We may have some more information on that. That was the aim of my question, because it seems that it works quite well. Because usually the dissipation is always a problem for us, but in this case, the first experiment were quite okay. So, well, we go ahead and we'll talk about that when you.
Yeah. So were these experiments with Vincent Pagneux?
Yes, it's
okay. Yeah. So he showed me some of the preliminary results.
Yes.
And they looked very good. I mean, there was a bit of, there was a bit of dissipation.
Yes.
But that's always the difficulty with water waves, is fighting all these other effects like surface tension, viscosity, vorticity, non-linearity. It's always difficult. I'm always very impressed that people manage to get anything decent out of water wave experiments.
Well, thank you anyway for your talk.
Okay, yeah.
Very interesting.
Okay, fantastic. So anyone else wants to ask a question on the theoretical or experimental side? So I think we had like 40 minutes of questions. So that's great. Well, let us thank our speaker again.
Merci.
Lovely talk, Richard. Both, I said, for applied mathematicians like Ori, and
I'm back again. I can see everybody.
Experimentalists. So, Bogdan, who will be our next speaker next week?
Next week we'll have Alexei Maznev from MIT in Boston.
Okay, so that's great. So I hope you can join us again next week. And so this talk will be made permanently available anyway. So, please not hesitate to let people know that they can watch this wonderful talk later on. So thank you so much, Professor, for this wonderful talk. That was great. Thank you very much.
Thanks for inviting me. Thank you.
Bye. Bye.
Thank you. Bye.